perhaps open the slides.
Good.
Good. Good morning, everybody. Nice to, I cannot see you, I cannot hear you, but I can feel your presence. And if you would like to chat, your questions, whatever comments, I really appreciate, because I miss the audience, and that affects my presentation. Today, we will talk about, as it stands, radiation and matter. Central concept of this lecture would be transitions. Since we are talking about radiation and matter, that will be transitions of emission and absorption. In the previous lecture, we have quantized bosonic fields, classical fields. It could be electromagnetic radiation. It can be any field, any thing which we can see as a big set of harmonic oscillators, like strings, phonons in solid, all kinds of oscillations. There are examples of the fields. And we will try to keep the same generality in the beginning of our lecture. First, I will talk about golden rule, which enables the concept of transition, which gives us possibility to compute transition rates. That will be in homework. So 2 last packages of homework will be mostly about transitions. Then I will try to talk about emission and absorption, keeping the same level of generality, not just saying it's electromagnetic field. I would just look at arbitrary boson field. We will compute these rates for a general system. We will compare this to understand the relation between emission and absorption, and we will derive or whatever, establish a couple of master equations. So it won't be quantum mechanics. It won't be stochastic equation describing transitions. we'll get a couple of master equations, one for matter and another one for distribution of photons within a mode. Right, classical example, which was very important for development of quantum mechanics in very beginning, is black body radiation. So we will look at black body radiation. Good, that will be about transitions. Then there will be a little bit separate topic. You see it is given by different color. I will derive interaction between matter, charged particles, and electromagnetic field. This interaction can be derived and eventually has to be derived with a certain gauge trick, which relies on fundamental symmetries of quantum mechanics. Right. Then we will talk about different manifestations of radiation, and I will talk about electromagnetic radiation. We will talk about atoms, and blue glow, it's electromagnetic emission by free electrons. Good. What is the point? Normally, I don't have time on this topic, so they are very sketchy. You could, of course, read the book. It's always a possibility, but still now we are in a bit unusual settings. We can take advantage of this. So what I will do, I will read the lecture in normal pace. So these two will be very sketchy. I will talk more about lasers because it's important. Then I happen to have some time after the lecture. Well, you perhaps are busy with other subjects, other lectures. I have some time. So after I officially finish the lecture, and you may go, of course, I will turn back to these two topics, and I hope I will give some more details about this. All right, topics are many. Let me start. Let me start with most important starting topic is golden rule. Let us see, how does it go? Right. So.
Right.
Is there anything in chat? Let us see. There is nothing in chat, so there's no questions. I hear somebody talking at the background. That is a bit disturbing. Let us see. No, I guess it's fine. Good. So remember questions to the chat. Fermi Golden Rule. Strangely enough, it's not due to Fermi. Fermi just wrote a book about this rule, about this application. That's why it's called Fermi Golden Rule. Actually, people think that it's due to Heisenberg. Right, and let us understand what is the outcome of this formula. this gives us transition rate. We think of a system which goes from initial state to a set of final states. If you consider probability for the system to remain in initial state, right? Due to this transition, it will become smaller and smaller as a function of time. And the derivative of probability with respect to time, probability change per unit time, which in English is called rate, is just given by this formula. Gamma is the rate. What would be Dutch translation for the rate? I was pretty much astonished when I learned Dutch to learn this. This is actually, let's see, verandering van waarschijnlijkheid per tijdseenheid. That long is this. Anyway, right. So we understand what is this. If my explanations were not enough, if somebody doesn't understand what is the rate, I would be glad to outline once again, put the question to the chat. All right, great. So how to compute this rate? There is a formula for this. One can derive it, it's derived in the books. One can get the derivation from many sources. The derivation is involved because it's not really Schrödinger equation. Schrödinger equation doesn't have any transitions. One really has to concentrate on probabilities to compute their changes. And these transitions arise from a part of the Hamiltonian, interaction Hamiltonian. So a golden rule is in fact a perturbation theory. Like we have computed perturbation corrections in our homework for energies of the levels. Here it's a transition rate which is given by perturbation. Fine. So what's the formula for that? There are probabilities per time. There are rates to go to all the states, and the total rate is a sum over all final states. Right. And what do we have for each? We have a squared of matrix element of interaction between initial state and each final state to the second power. And in addition to this, we have a very important and somehow strange element. It's delta function of energy. The message is that energy must conserve in course of the transition. So the energy of initial state must be the same as the energy of final state. But then it becomes a little bit crazy if one takes this formula as it stands. Why is it so? because of this delta function. It says if there are energies of two states, initial and final states, they differ just a little bit, there is no transition. And if by chance they are aligned, the transition rate is infinite. So this formula, in distinction from many formulas given to you, is not immediately meaningful. To make it meaningful, we should sum over infinitely many final states, assuming continuous spectrum. Right, let me make a small drawing illustrating this. So this was energy. This is energy of initial state, right? And let me sketch it perhaps with different color. Ooh, cannot get color correctly. What is this? Yeah, energies of the final states. If I put that in discrete fashion, there is not much of energies transition rate is 0. But if I carefully go to the limit of continuous spectrum, well, I can always find a state with matching energy. So this will amount in a final rate. So a continuous spectrum of final states is very important here. It enables the applications of Fermi Golden rule. Good. So what is a typical situation of application of Golden rule? Suppose we have an atom in excited state and there is a transition. Atom goes to the ground state and it emits a photon, and the energy of this photon should match the energy difference of atomic levels. Photons are characterized with K vector. So in principle, possible final states differ by wave vector of the photon, and one has to sum up over all these possibilities. So summation in this formula would be over K. After this is done, one would have to replace the sum, as we did already many times. One will have to replace the sum with integration over K and integrate delta function, which is there. We will make it explicit in several minutes. All right, in this case, it works. It gives us final answer for the rate. And again, the reason for that photons have continuous spectrum. Fine, that was about Fermi Golden rule. Important general subjects. That is valid for transitions of any kind. And let me just make one step to a more specific situation. Don't see anything in the chart. Are you alive, guys?
Yes.
Okay, good. Good, 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 good. Thank you. Fine, sir, let me go to more specific transition. We will consider matter and radiation. We don't want to be very specific of the matter. Let's think of atoms. Let's think of two discrete states of an atom, for instance, state A and state B. Next, and let's see, A is going to be excited state. The energy of A is bigger than energy of B. Right, then we have photons over whatever phonons, oscillations of a string. We have classical fields, we have quantized it, and we have a bunch of bosons. Right. Then interaction between matter and bosonic field. I can write in terms of field operators of this field, right, which I would call X. Look, X is a linear function of creation and annihilation operators of this field with some coefficients. I don't want to specify it at the moment because for different fields, these coefficients will be different. So this operator acts only on, let's call it radiation, on this bosonic field, while operators M, as the letter suggests, are operators which act on matter. So there are two subspaces in the full Hilbert space of the system. That's matter, that's radiation. This works only in matter subspace. This works only in radiation subspace. Good. So as we will see, we have here summation over Q, which labels the states of the photons. And right, we can set apart the processes which involve different Q's. So we can, let's concentrate on a process where Q is certain. So we know with which boson state we operate. Right, let us understand what are possible initial and final states. First of all, absorption. So initially, the system is in a ground state. And also, in addition, there are some bosons. How would I characterize the state of this boson? Just with a number, with occupation number of this particular mode with certain Q. Good, that's gonna be initial state. Let me consider what are possible final states. Right, so I will have to go to excited state, so that must be a matter. And in addition, all right, I have to get some energy. to go from lower state to upper state. So I have to absorb a boson from this mode. So I will have in final state one boson less. That is absorption. As to emission, it just goes the other way around. So initially, we are in excited state, and we have some number of bosons. Then one needs to emit one to get rid of extra energy at this excited state. So the number of bosons is increased by 1. Fine, good, it's all straightforward. Let us see. Let's go to work and let us apply Fermi Golden rule. So for this, we need to compute matrix element. Yes, there is a question. The question is, are the bosons coming from the matter? Bosons and matter are separate issues. They have separate Hamiltonians, separate degrees of freedom. Right. So again, talking about our examples or atoms, which are matter, the radiation are photons. Coming from, yes, one can say so. This is the issue of a transition. So as atom in excited state, it can interact with boson modes, and the result of this interaction is emission. So the atom goes down, and the boson is added to all bosons in the system. Does it answer your question? Good. Good. Let us talk about matrix elements. Basically, my idea is to compare matrix elements for absorption and emission, and compare and get some relation between these two. Well, it just works. So we consider absorption, final state, initial state. We have separation between operators which work on bosons and operators which work on matter. That's why matrix element we can rewrite in this form. Good. So this is fixed. What is the sum over A? There are multiple operators in matter which can be connected with multiple field operators. For instance, when we talk about atoms, those will be 3 components of electronic current, and those will be 3 components of vector field, of vector potential of electric field. I don't want to write X, Y, Z. I don't want to specify it at the moment. It's enough to say that there's a sum over multiple operators. What is important, again, that there is a relation between these matrix elements. Good, so sum over A. Right, then we just This is, we consider this, we computed, we consider this known, that will become MAB, this index A. And that, again, this X is a coefficient within the field operator. We have it here. And then we need to, since it's going about absorption, we need to compute matrix element of annihilation operator between these two states. Yeah, we remember the definition of an operator. That will give us NK. All right, we need matrix element squared. So we have NK in front of it. Good. Let's think of if you can understand it physically, correctly or not correctly. Absorption. In order to absorb a photon boson, one has to have it initially. So the more we have, the more we can absorb. This is natural. So absorption is proportional to number of photons in a mode. So what about emission? Well, we run the same calculation. The only point we need to compute an operator of creation, right? And that will give us square root of 1 plus n. And finally, we have it. We have the relation. So whatever the interaction, the ratio of these two elements will only depend on number of photons, number of bosons in a certain mode, in a mode with which we interact. Fine. Let us get to transition rate from the squares of matrix elements. Let me first consider partial rate. Partial, it goes to or from a certain wave vector, certain label K. Good. So what we will have for absorption and emission, again, we need to assume that energy of the boson matches the energy difference. Right. So we get the relation between the rates of absorption and emission, and that will depend on number of photons only. But well, how would we know the number of photons? In principle, it is different for different modes. But we kind of average over this mode. So in fact, we average over all K, which satisfies this relation. Over all K, when a photon boson has a certain energy. So with this, we can replace integer n with some fill-in factor. Fill-in factor specific for this energy. Right? Thereby, we get the relation between emission and absorption. Right? For mostly historical reasons, the emission is separated onto two parts. Let me explain this. Perhaps it's instructive. If we talk about absorption, absorption is proportional to number of bosons available, and this is natural. If we talk about emission, all right, it can happen even without any photon available, right? It's called spontaneous emission. And kind of a very wild guess would be that this rate does not care about all other bosons which are in this particular mode. Could be, might sound logical, but it's not what we computed. And it is not what one can assess from more consistent reasoning. In fact, there's also what is called stimulated emission. So if there are many bosons in the mode, they help the atom to decay faster. And one can say that lasers are based on this principle, on the principle of stimulated emission. Good. There words. The separation is a bit artificial, but well, it has clear meaning. Good. So we cover spontaneous and stimulated emission. I'm doing with respect to time. Not that bad. Well, let me now establish a couple of tools with which we can understand the situation when transitions happen. Right? The tools will be simple, but in order to make them, one needs to depart from purely quantum mechanical reasoning. So instead of a wave function, which might depend on many parameters, many degrees of freedom, we rather go to probability to be in a certain state characterized by these parameters. Right, so you'll be talking about probability to be in certain states. Wave function is forgotten. And right, transition rates will give us, by their definition, probability change per unit time. So generally, what we get are evolution equations for probability. Good. Let us first understand master equation 1. And this is, again, I have this system or collections of the system systems. Some of them are in the state A, some of them are in the state B. And I will look at probability. So to derive master equation, I don't have to do much of calculations. A master equation approach is very similar to bookkeeping. So it's about bookkeeping, it's about taking into account all possible processes, all possible transitions, which can happen in our system. Good, so suppose initially the system is in state A. So what can happen? Well, first term, which comes with a minus sign, is a probability to go to all other states. All right. This happens with this rate. Let's see, A is excited state, so this is absorption rate. Do I have it correctly? Yes, it's absorption rate. Fine. And this is negative. So the system goes from state A to all possible states. But there are also processes whereby the system is initially in state B, and there is emission process, which brings it to state A. And well, this is positive contribution. Good. Similar equation with the same reasoning we can derive for probability B. Now it is always a possibility of error, right? There is a very simple foolproof for master equation. Let us see, let me erase all this. Well, to make foolproof, let me just add this too. Right, what I have on the left-hand side, it's a time derivative of total probability but this is one and it will not change. So that must be 0 on the left-hand side. Let me check if right-hand side goes to 0. All right, if I sum up, I can cancel this term and this term, this term and this term. Good. It is we have proved that it satisfies this simple relation. Good. Master equation 1. It describes the probabilities in matter. Let me have another equation. And this will be for probability to have certain number of bosons in a given mode. Okay. K is a given mode. Sir, how can I derive master equation for this situation? Let me start with negative terms, what bookkeepers call expense. For a given n, I can have processes with emission and absorption which change n by plus or minus 1. So I will bring these rates over here. All right. Positive terms. Initially, I could have n minus 1 transition. I have a contribution to change of probability at n. Or initially, I have to be an n plus 1, n plus 1, and then let's see, absorption. I can go to another state. Right, I made these coefficients red to stress that they're not the same as here and here. Why is it so? It's because I have different number of particles initially. Once again, emission and absorption rates, they depend on number of bosons in a certain mode. Good. So what is obtained here are master equations for matter and radiation. Usually we don't want to look at time-dependent solution of this equation. Usually we assume kind of equilibrium where all these probabilities are stationary. Then it becomes an equation for probabilities because all derivatives here, here, also here, they will become zeros. Right, there is a question from Angeline. Let us see. I don't really get why we use the absorption part multiplied by PA for the state that makes the transition from state A to state B in master equation 1. Perhaps there is a mess up. Let us see. Let me get to this scheme. We go from A to B, and this is emission. When we go from B to A, this is absorption, right? Let us see if I have it here correctly. So this is, perhaps I mess up excited state and final state. Sorry, mess up excited state and ground state. Let us see what is written here. It goes from state A, and this is absorption. Okay, so A here is the ground state. And B is excited. So I just change the labeling of the states. All right, is it fine now? Let me check it again. So from this state, I go out with absorption. So B is excited state. Fine. Let us see. Right. Let me look at the timeline. Okay, I have a little bit of delay already. Let me talk about black body radiation, and then we'll have a break. Good. So let us assume that matter is in thermodynamic equilibrium. What does it mean? It means that the probabilities to be in these two states are fixed by Boltzmann distribution. So they don't depend on anything but energy and temperature. Fine. Well, we don't know what are these probabilities, but we can compute the ratio of these probabilities immediately, right? So there will be just ratio of filling factors, and the ratio will depend on energy difference between these two states. Let us substitute it in a master equation and figure out what does it imply for radiation. It follows from master equation 1 that the ratio of these probabilities is just the ratio of emission and absorption rate. Perhaps it's not obvious. Let me spend a second in explaining this. All right, so I take this equation, I put 0 here, then I can sort it out like having and gamma PA in this side. And this side. Now I can divide it by B, and I can derive it by this, just transferred here. So there is a ratio of the rates. Ratio of probabilities should be in stationary state should be the same as ratio of the rates. Good, but these probabilities are determined from thermal equilibrium, which means that the ratio of the rates will depend on the energy of the boson involved and temperature. From the other hand, we know what is the ratio of emission and absorption rate. Average number of particles for absorption, average number of particles plus 1 for emission. Good. So from this, we can compute average number of photons in a given mode. And look, all trick, it becomes Bose distribution. Yet another way to compute Bose distribution. Well, from the other hand, we can obtain the same result in a different way. And we can look at master equation 2 and understand when we have equilibrium within the amount. And that will happen when this will hold. So probability with n to have n photons and emit those must be the same as probability to have n plus 1 and absorb n plus 1 photons. Otherwise, there is no equilibrium. Good. That also gives us the ratio of the rates, namely the ratio between probability with n plus 1 and probability with Pn, and this is constant. Good. That we can solve and find probabilities to be in a state with certain n. And look, we have reproduced Boltzmann factor here. So it's all consistent. Solutions of master equation reproduce the results of thermodynamics for us. In this case, we talk about temperature of matter as far as temperature of radiation. Good. Let me talk about what was actually the start of quantum mechanics, what was the work of Planck about black body radiation. To do so, we need to derive what is called law of Stefan, which has been kind of empirically established. Now we can have some theory for that. What we want to do is to consider matter which is characterized by certain temperature. This matter will emit phonons, which will go to the right. There will be no phonons going from the left. There will be nothing there. Then it means that we have a flux, we have energy transfer in this direction. So how to compute them? I need to sum up our photons with all possible indices. The only point I have to make sure that I look only at photons which go to the right. That gives me this zeta function. Right, and I know the distribution, Bose distribution of these photons. And I know the coefficient which defines energy flux that we have derived when we talk about Poynting vector, when we talk about irradiation. Or I guess I have a problem with camera. It took me quite some time to understand. Fine. So we can compute the flux. And that will give us probability that will give us, eventually I have to look at the flux per unit per interval of omegas, per interval of frequencies of the photons. All right, so it contains Planck distribution, and it is given by this red line. Fine. This is can be integrated. It gives finite flux of black body radiation coming from us from a body. It is finite. But this because of Planck, because he kind of conjectured that the function here is a Bose distribution. Looking at things classically, one would rather write classical approximation for this Bose distribution function, which will be kbt divided by h omega. This is what classical physics without h bar would do. And okay, as a function of omega, it is given by this green line in the plot. And that means that the energy flux is eventually infinite. There is no way a body, for instance, a star, can keep good. Let us see. To warm up, I have a question about the breaks. Actually, we got some general recommendations from education services, how to proceed with online education. And one of the recommendations was to have more breaks, shorter periods of concentration. But that's, of course, very general. I don't know, how do you feel about it? So why don't you give your opinion about the following? Shall we have 2 breaks during the lecture instead of a single break? So please type yes or no in the chat. No, no, no. Yes. Oh, that's something with my camera again. Good, sir. For most students, the answer is no. And there is a general feeling that that the breaks should be longer. Fine, this is the message. Although there are some people who said yes. What's going on with my camera? I'm sorry. Let's see. So I hope it will be better now. All right, so we still keep to one break, but yeah, I have to do better with respect to time schedule. I will have to make it longer. Fine, let's go on. Let's go on. And now we switch the gauges and we go to gauge transform. It's very fine way to actually derive interaction between matter and radiation. Sure, let us start with a Schrödinger equation for a particle. For simplicity, I don't want to have any potential. So it just has kinetic energy term, evolution equation. And let's make well, I would say, I would even have to say, let's have mathematical transformation of this. Let us multiply wave function with a factor, phase factor. We know that phase factor doesn't affect probabilities. So, we just put this wave function into this equation, and we will obtain that this will satisfy new equation, transformed equation. Time derivative of chi will be here, and the gradient of chi will come from the gradients over here. Fine, mathematically it doesn't mean much, just one mathematical representation against another one. Physically, it means a lot because now we are playing gauge trick. Namely, we identify this transformation with the gauge transformation of the fields. We know that we can also change vector potential and scalar potential in an arbitrary fashion, keeping electric and magnetic fields the same, right? And this is a transformation. So we want to have same chi here and here. And we want to add the fields into Schrödinger equation in such a way that this transformation disappears from equation. Right? And that amounts to substitution, wrong substitution, so to say. So instead of time derivative of chi, we would put scalar potential. And instead of gradient of chi, we will put vector potential. Good. And that will give us correct equation for a particle with charge E. E comes here and here. In electromagnetic field. So we understand how electromagnetic field affects equation for a single particle. Right. To make it a little bit mnemonic, people talk about derivative elongation. So each gradient which comes into this equation, it gets addition proportional to vector potential. Time derivative is also changed, but with a scalar potential. What is going on today? I'm sorry. If it happens again, I will switch to another camera. But that's a pretty much convenient one. I would prefer like this. Fine. Gauge transformation. So that was without second quantization, but we can easily get to second quantized form of this. Well, because we know the Hamiltonian and we know how Hamiltonian is modified, and we know how Hamiltonian will come in second quantization. Good. So we have both potential, scalar potential, and vector potential in the equation. And there is now a separation, which is a bit artificial, but in fact very much useful for studying radiation. Namely, we will use Coulomb gauge, and we will incorporate potential over here to instant Coulomb interactions, right? So we will write the potential in the form of potential which is made by electrons, which is instant. And with this, we can write what we have already, Hamiltonian with interaction. And we will forget about this I. As to vector potential, we will keep it. And that will be terms describing interaction between radiation and matter. So there was the same Hamiltonian. And with all other physicists, a little bit artificially separated it in three terms. These terms go to matter. Part of this Hamiltonian which doesn't depend on fields plus interaction, that all go to matter. There's also a Hamiltonian bosonic Hamiltonian of non-interacting bosons, which describes radiation. And there is interaction term, right? So it contains first power and second power of A. Commonly, second power effects do not matter. So if I concentrate on the first power only. Let's see what to get. Oh, look, I get very convenient expression, easy to memorize. Has also advantage that it is also valid in relativistic regime. So far, I didn't think of relativity in my derivations, but well, if I keep it like this, this expression is also valid for in relativistic regime. And what is the expression? It's simply made of operator of radiation, field operator of vector potential, and operator of current density. There was a question about summation over A in the beginning of the lecture, right? So here summation comes from scalar product. So all these things are vectors, these components x, y, z. So A goes through x, y, z in this case. Good. Operator of current density. All right, we can use operator of current to make it and promote it to second quantized form. So here it is, operator of current density. I can also write it without second quantizations, just acting on wave function of several particles. What does it mean? So the current density at the point R, well, in order to produce current density, the particle must be in this point, right? So there's a delta function. And then the density is given by velocity of this particle. Good. So in fact, the interaction is simple. We just need to know operator of vector potential A and operator of electronic current density. Fine. Let's see. No questions so far. So basically, I covered, I've derived the interaction with the gauge trick. And yeah, that's a relatively short expression we have ended up with. Now we can apply it to study the transitions with emission and absorption. Right. Let's talk about atoms. Let's talk about atoms. Let me consider a typical situation of an atom. In this case, the ground state of an atom usually corresponds to S state. Let's talk about hydrogen atom for simplicity. So it has only one electron, which is in its ground state is in S state. So this is spherically symmetric state. Then the excited state we are interested in is pi state. Eventually, there are 3 pi states. It doesn't matter for us at the moment which of the 3 it is. Right, so we will look at spontaneous emissions by atoms, and I wonder if I have a couple of minutes for some quiz. Yeah, perhaps I have a couple of minutes. It's about general physics, very general physics, something which you perhaps got in your course of whatever it's been called, everyday physics. It's time to recall it. So here I gave 3 spectra. And the lower one is emission spectrum of the atoms. So I have gas of atoms, which is excited up to some temperature. So, and these excited states, they give tiny spectral lines. And, you know, the observation of these spectral lines gave people the idea that there are atoms, discrete energy states, and actually led to quantum mechanics. Right, but this spectrum is not commonly seen. If we just look at the sun, the spectrum of sun is eventually black body radiation. So in very good approximation, this continues. No, I guess we have a contradiction here. Namely, the sun consists of atoms. So eventually I would expect discrete lines instead of continuous spectrum. So why is it so? Why the observed spectrum of the sun is continuous? Who can answer? Please answer in the chat. Once again, the sun, our star, is like, if I remember correctly, like 70% of hydrogen and 30% of helium, is a very small amount of other elements. It consists of atoms, so one would expect discrete spectrum, but the spectrum is continuous. All right, good. There are 2 answers. First answer. The sun is a plasma, so electrons aren't bound to atom states. Second answer, because of interactions between the atoms and overlap of their wave functions. Good. Both answers are in good direction. Just let me a little bit specify. Indeed, the sun is plasma, but it depends where in the sun you are. And plasma would mean that electrons and protons are completely separate. Eventually, in most of sun matter, it's not so. Electrons still stick to you still can't say, no, this is hydrogen atom, this is helium atom. There is still a separation. But it is sure that this gas is pretty dense, and interactions between atoms become important. And due to this interaction, atoms can emit at any energy, because it's not isolated atom which can lose energy only by a discrete portion. It's already a system of the atoms which can which is much more flexible with respect to possible energy losses. This is why the observed spectrum is continuous, but nevertheless, the first observation of spectral lines was already in sun spectrum. And these spectral lines have been seen as black lines. Nor light is coming in this narrow spectral interval. So now, who remembers the explanation for this spectrum? Why is it so? Yes, absorption. By what and why? Yeah, it is atmosphere over thermosphere. Yeah, okay. All questions to kind of go to good direction. Indeed, it's an absorption. It is an absorption, and in order to absorb, the atoms have to be cold. They have to be in the ground state. Right, what happens, there is a part of sun which emits, which really at high temperature. And there is also kind of a distribution. So it's plenty of the gas, which is already very rare, which the atoms, they don't interact, and they are already cold. They are at some distance from the sun atmosphere, one can say. And absorption actually happens there. Good. That's why what we see in the sun are hydrogen and helium lines from these stray atoms, which are already at some distance from the sun, which are already cold, so they can absorb. Very good. Very good. Then let us see. Let us understand what do we need in order to compute transition rate for this situation. Let us concentrate on this situation. Anyway, we know the relation between emission and absorption. Spontaneous emission would suffice for our rate calculation. So we assume no photons around. Transition rate is given by, well, I need to sum up overall possible states of the photon, the emitted photon, okay, and also polarization. Energy must be conserved. And right, I need to find the matrix element of emission of a photon with a given wave vector. Right, so those are initial and final states I have. Let me stress again that there are many final states, eventually infinitely many. Only in this way, application of Fermi Golden rule makes sense. So this is why I almost immediately replaced summation by integration over K. Good, so then we need to compute this element, and in order to do so, one needs to make an approximation. It's not an artificial approximation, it comes naturally, so it has to be implemented. It is called, again, dipole approximation, again, from some historic reasons. What does it mean? This is general interaction. And here we have density of electrons, which depends on, density of the current, which depends on coordinates, and vector potential, which depends on coordinates as well. Let me compare the scales, spatial scales for atoms and for radiation. Atomic states are concentrated on a small radius, Bohr radius, like 1/10 of nanometer. If I look at the wavelengths, which corresponds to atomic energy, that would be at least 1,000 times bigger. This is why one can neglect spatial variation of vector potential at the scale of the order of Bohr radius of the order of atomic scale. So this is the dipole approximation. So I just take A in a certain point in the center of the atom. All right. So now I can separate matrix elements. So this is a matrix element which comes from A. You might remember ugly coefficient, which comes from field operator of vector potential. It's a vector. So the polarization of the field enters here. Good. As to this operator, well, we integrate it over R. So instead of current density, we have total operator of the current. And this is for non-relativistic particle, it just velocity E over M. Fine. Let's go further with the evaluation of the Hamiltonian, of the matrix element, sorry. There is a convenient way to compute matrix elements of velocity. Eventually one uses Heisenberg formula for that. And in this way, velocity is equivalent to commutator of Hamiltonian and coordinate. For matrix element, this Hamiltonian just gives the energy difference. So one needs to determine the operator of coordinate. Actually, that gave the name to the approximation, because this is dipole moment. This is dipole moment corresponding to a transition between two atomic states, A and B. Good. Now one can collect all this and get for square of matrix element Well, there is a scalar product of two vectors, vector of dipole moment and polarization. There is also a factor. Good. We need to compute dipole moments. Let's see. No, let's see how much time do I have. Oh, Jesus. Good. Let me postpone this technical discussion. As we agreed, I can talk more about this after regular lecture. Let me finish this lecture. So I just go through transparencies. Kind of the message is that one can compute this rate, and it appears to be small. It contains our famous small parameter fine structure constant alpha 10 to the minus 2. Eventually, implying dipole approximation, one estimates that the rate divided by atomic frequency is alpha to the power 3, and this is 10 to the minus 6. So the atomic states live incredibly a long time. Excited states, it's 1 million time longer time than the typical atomic frequency. Fine, good. I skip selection rules and computation for hydrogen atom, and I skip everything about Blue glow. To talk a little bit about lasers. All right, I want to keep it short, but I think I need like 15 minutes. Sorry for this. Lasers. Here in this picture, one sees a typical laser setup. It's a gas laser. It's, let's see, neon helium laser, I believe. And one sees of lots of light in this picture. And my question, perhaps it is naive, perhaps not. What color is the laser light in this picture? Any of you still alive? My question was, what color is laser light in this picture? Yes, very good. That's green. That is green, undoubtedly green. So very concentrated beam, which somebody uses for experiments, is of green color. And there's very little of green light. Eventually, there's much of orange light. So let us understand why this happens and what is the mechanism of the laser. Perhaps you have heard about this. It's also kind of discussed in everyday physics. The lasers are roughly, so cartoon about the laser is stimulated emission. So if an excited atom gives rise to a photon, did I say photon? Yes, I said photon, which can be kept in a certain mode. Next atom can emit with eventually bigger rate, and it will send yet another photon. Again, if it is accumulated in this mode, it will increase emission rate even further. So it looks like a chain reaction. Good. Whatever the cartoon, it gives us correct requirements to have a laser. First of all, there must be a way to produce and keep the atoms excited. If they're not kept inside them, it would be just, flash of light and all atoms in a ground state. Right. In practical lasers, they are like in this laser, they are excited with electric discharge. That's what one sees here in this tube. It can be also non-laser light, can be electricity like in lasers which you see in supermarkets. Another requirement, one has to keep the photons in the laser, because if they go away, you don't have stimulated emission. So in this laser, this is solved by putting half transparent mirrors at the end of this optical tube. Fine. Let us consider the processes in this laser. So this electric discharge, atoms are excited, and they are excited at a certain rate, number of atoms excited per second. What is specific for this helium-ion laser, that it's helium ions which are predominantly accelerated by this discharge, and when they're excited, it's a very good match of excited state of helium atom and certain excited state of neon atom. And there are transitions, energy goes there, and there are transitions in neon atoms. And most transitions just go to set of lower orbitals, and they give this orange light. However, there is one specific mode, which is lasing mode, which is green in these circumstances. And for this mode, the decay is stimulated. What does it mean? That we can arrange significant number of photons in this mode. That doesn't work for orange modes because this light is gone. Fine. Sure, what we can do, we can write down master equations. Again, two types, for matter and for irradiation, for photon distribution within a mode. First of all, for matter, this is number of excited atoms. So those is increased at the rate R, and it is decreased by non-stimulated emission and stimulated emission to a given mode. The average number of photons, I need to take the number of excitations to this mode. Also, I need to take into account losses from the laser mode. Here it is. So traditionally, I introduce quality factor for laser mode and write the frequency of this mode comes. So this is just losses, the photons that leave the lasing mode. Right. And this is for photon distribution. Let me address it in several minutes. Let me talk now about the first two equations. Let me talk about gain and saturation in the laser. Well, I can figure out number of excited atoms, and I can figure out the total emission from these atoms. How does it depend on number of photons in the laser? At small n, well, n is always bigger than unity. So if I plot it over n, I will see something which saturates at big N. Why is it so? Let us see, let me take a limit of big N. So that then I can neglect gamma and these two factor cancel. So saturation would be just at the rate at which atoms are supplied. Natural. Good. Then this emission should be equal to losses in the laser. Losses in the laser are proportional to omega q times number of photons. All right. So in order to find equilibrium number of photons in the laser, I need to draw a line at this plot and to find the crossing. It is sure that if the losses are big, the crossing is at 0 and the system does not lace. But at some critical value, when gain exceeds the losses, well, I have intersection with this curve. I have laser state. Sorry, I've taken quite some time. I hope some of you are still there. I wanted to finish my lecture with a rather strong statement or example, I don't know how to say. Now I can simple balance between emission and losses in the laser. We can find equilibrium number of photons in the lasing mode. Now let us make more detailed calculation. Let us figure out what would be distribution of number of photons in the lasing mode. So to this end, first I turn to a simple limit. I will assume saturated laser. So it is close to the 100% efficiency. And I will write the master equation for number of photons for their probabilities. Yeah. Right, so there are terms which come with minus sign, which allow transitions is increasing and decreasing of number of photons. Well, this is due to emission to the laser mode. This is due to losses, right? Good, and their respective positive terms. Again, this is emission. Initial state is n plus 1. And this is, sorry, the losses from the laser. This is emission to the laser mode. It increases the number of photons. Very good. This equation and stationary conditions can be solved by detailed balance method, like we did for equation describing black body radiation. However, the answer is different for that. You still find the ratio probabilities, and that will be proportional to the average number of photons in the laser divided by n. That we can easily compute step by step, right? The resulting distribution is called Poisson distribution, distribution of independent events. Comes in different areas of physics. Good. It makes sense to assume big average number of photons in the laser. Otherwise, it's not a laser. Otherwise, yeah, one can hardly see any photons coming up. Let us just look at this distribution, right? Eventually, it can be at large, and it can be approximated by Gaussian distribution with a spread proportional to number of photons. So here it is. We see that the distribution is centered at some big number, 300 in this case. And there is a spread, which is still appreciable. What does it mean? What does this imply? In this case, at a given model, there's a certain number of photons in the laser. Owing to transitions, this number changes, fluctuates. It's kind of go back and forth in this region. Sure, one should see fluctuations in laser light according to this picture. And this is not so. Absolutely. To understand why it is not so, we will have next lecture about coherent states. Here I should just stress that the calculation is pretty much correct. And this is indeed a distribution of number of photons in the laser. But the fact that this number fluctuates and is certain at a given moment of time is not correct. It comes from our classical intuition, which is not applicable to laser light. So we will discuss this in a week in a lecture about coherent state. Fine. So now I have finished the main flow of the lecture. Let me come back to the topics which I have missed. Let me tell you a bit more about atoms, emission from atoms. Let me also shortly tell you about the emission of electromagnetic radiation by free electrons. Let us see. Need to go back, quite some transparencies back. Right. Let me come back to this transparency. What did we do here? The purpose is to calculate matrix element between initial and final states of interaction between matter and radiation. This matrix element can be separated into parts. Matrix element of current density is just between matter, it's separator of matter, while this is solely about photons. So we can compute matrix elements separately. So here we have ugly square root, here we have polarization vector, same vector here. This is better to reduce to matrix element of dipole moment, matrix element of coordinate. It's still vector. With this, we have the following expression for the square of matrix element. Here we find matrix element of dipole moment. We find polarization. And okay, there are coefficients coming from here and here. Good, let's go further. Let's, oh, wrong direction. Let us concentrate on the rate in a certain direction. What is the probability to emit photons in a certain direction? That already something which we can compute. Let us see, this is partial rate, that's why I put delta gamma. Here the square of matrix element. Here there is a Dirac delta function expressing energy conservation. Energy of the photon is proportional to the modulus of its wave vector proportional to Q. All right, here I miss the fraction sign. So here it's an element of three-dimensional integration over Q. Good. Let's get it in spherical coordinates. So we have integration over angle, and we have integration over modulus of Q. Good. Now we can integrate this expression over modulus of Q. In this case, we integrate delta function. Whatever, let me put it simple. Right. And that will give, yeah, you should recall rules of integration with delta function. That would be 1 over h c. Fine, so we make this integration. What we have now is a rate proportional to the interval of a solid angle. Let us now turn to this point and understand the polarization of emitted photons. Polarizations. Let us see what would be convenient coordinate system to put all these three-dimensional vectors to. Let me have a vector in the direction of dipole moment. Right. Them for any direction of photon vector, we can introduce two polarization directions in the following way. One polarization is perpendicular to both vectors, and there is no emission to this mode. Why? Because, yeah, if it's perpendicular to R, this vanishes. There is emission in this polarization E1, and this is again by making in product is proportional to sine Q, theta being the angle between direction of propagation and the direction of dipole moment. Fine. So now we can make another step. We can specify angular dependence. Right. If one kind of plots the intensity diagram depending on the direction of Q, the maximum is for direction of propagation is perpendicular to this vector, and nothing comes in the direction of dipole moment. After that, we are interested in overall rate. So we integrate overall possible directions. All right, there's some geometry to do. This is integration over the angles. Right, so finally we get this expression. It's a rate of spontaneous emission, and right here it is. Let's try to make a sensible estimation of the value of this rate. How we can do this? Let us see. First, what is to estimate? Rate has dimension of frequency. And to make it dimensionless, I would compare it with a typical frequency of atomic state. Basically, the energy which we have just emitted. Right. And I estimate this value, which is in fact like inverse quality factor, how many oscillations an atomic state does before it decays. Right, so we have this alpha, which we got already, a small factor, and we have eventually a factor which is small in view of dipole approximation. What we find here actually is the ratio of dipole moment to wavelengths. It's also very small. It can be estimated with alpha. So in total, we have estimated this rate in dimensions units as alpha to the power 3. So it's about 1 millionth. Right, what does this imply? It implies that the excited atomic states live long. Typical frequency omega is something like 10 to the 15 hertz. Typical gamma, we need to divide it by 1,000,000. That would be like 10 to the 9. Did I do it correctly? Yes. 15 minus 6, that's going to be 9. Much longer time scale. Fine. Now we need to evaluate dipole moment for a transition between two atomic states, A and B. So how do we do so? Atoms are spherically symmetric. So before computing this matrix elements, we want to make sure that we are not computing zero. Yeah, it is might be a rather interesting activity to compute zeros, but our appointment that in this case, we do our best not to compute zeros. So we need to look at symmetries. We need to look at representations of the symmetry groups to figure out and under which conditions this matrix element is zero. Good. What is symmetry classification for atoms? The potential which an electron feels in an atom is spherically symmetric. And all states in this setup can be characterized with 3 numbers. I don't know how much atomic physics do you take. I presume there was some story about atoms in your bachelor education. Fine, what are the states? This is orbital number. This is a number which represents the total angular momentum of a state. So it can be S states, pi states. This momentum is 0, pi is 1. And besides that, the states with the same angular momentum are degenerate to L plus 1 is the degree of degeneracy. So there's a single S state, there are 3 pi states. And right, it's a projection of momentum on that axis which separates the state. Right. One electron wave function hydrogen atom can be written as its radial part and a part which depends on the angles. Radial part does depend on details of the atomic potential. This doesn't depend on anything. It is universal function. It only depends on the angular momentum and the projection. Fine. I'm talking about selection rules. And what is the selection? The selection is to select a pair of states, a matrix element between two, the two is not zero. Right, so here present selection rules for the spherically symmetric potential. So the matrix element is only non-zero for transitions between different angular momenta, but not between arbitrary values of angular momenta. The values of angular momenta should differ only by 1 plus minus 1. As to another selection rule, we can choose again the vector of dipole moment in that axis, and then that will give corresponding change of delta m. So these transitions, if for vector parallel to z, these transitions are activated, and they correspond to waves with two different circular polarizations. All right, so there is a spectrum of typical atom. There are several S states, several pi states, and you see the degeneracy. And here I indicated possible transitions. So it can go, for instance, from D to T and then from T to S, but it cannot go from D to S directly. Right, so selection rules for transitions in atoms. And now one can do calculation, which has been done many years ago at the early days of quantum mechanics. Calculation for hydrogen atom. For hydrogen atom, the wave functions are pretty much known. And one can compute this matrix element for different momentum changes for different m's. This is angular part, and there's also radial part, which is different for states which differ by n and l. Right. Finally, one has to sum up over all possible changes of all possible changes of the number m. And one can express this rate in terms of matrix element, which involves only radial functions. We still have to elevate this matrix element. All right. And that can be computed already from the form of the answer. One sees that the calculation is pretty much involved. Oh, it can be done. People have done it like 80 years ago. Right. Hydrogen atom also gives us very certain value of the transition. So we consider the transition between 2pi state, excited state, to 1s to the ground state of hydrogen atom. And yeah, that's very accurate formula. This rate is known with high accuracy. Corresponds to our estimation. It's about 10 to the 9 hertz. Good. These selection rules are tricky. Let me finish the story about atoms with a simple consideration of the selection rules. Eventually, for hydrogen atom, 2 excited states, 2s and 2pi, have almost the same energy. Let us suppose that by some chance we got an atom into S. It seems that it cannot decay at all. All right? Selection rules forbid that. There is no transition between 2s states. Something must be done. And there is an opportunity to arrange this transition with emitting 2 photons instead of 1. And okay, how to, let me roughly estimate the rate of this 2 photon process. There is also exact calculation, but that really involved. It has been made only in 40s of 20th century, I believe. Let me roughly estimate this rate as follows. We understand that 2 photons are emitted. So somehow it has to be proportional to the product of the rates of both photons. All right, so I write gamma 1 to the power 2. I need to keep right dimension. The only value of correct dimension, which is not the rate, is the frequency of interatomic transition. Good. So it's our kind of simple estimation for 2 photon transition rate. Let us see. So that was 10 to the minus 9. 10 to the minus 9 to the power 2, 10 to the minus 18. And that we estimated as 10 to the minus 15. No, 10 to the no, I did it wrong. 10 to the 9, so 10 to the 18. Divided by this frequency, which is 10 to the 15. Fine, sure, we get something like 10 to the 3 hertz. This is our naive estimation. If one does a calculation in a bit in accurate manner, there are also a couple of small numerical factors which actually reduces this by a factor of 100. So in fact, the correct estimation is, yeah, it's written here. It's about 10 hertz. So it's already a scale which is accessible to us humans. That's how long an excited atom can live. Well, again, if it is in a 2s state. Fine, that's all about atoms. Let me talk about emission of photon by a free electron. It's actually a rather interesting story with many interesting deviations. First of all, let me note that in vacuum, such emission is strictly forbidden by relativity principle. In fact, yes, if this emission would be allowed, it would mean that an electron which moves can lose energy. Okay, it will lose energy, so it comes to the rest state. But what is a rest state? What is a rest state in one coordinate system doesn't have to be a rest state in another system. It can have energy. So the ability to lose energy, the ability to come to the rest is eventually in contradiction with relativity. Good. The strict prohibition. However, as we once discussed, the properties of vacuum can be changed. Not always. They can be changed. The scale of atomic physics, state of, or the scale of condensed matter physics. And indeed, if one considers the electric medium made by atoms at low frequencies lower than atomic frequencies, the speed of light is smaller than the actual speed of light, that speed of light in vacuum. Good, which means that there can be electrons which go faster than this speed. And they can emit the photons. This phenomenon, it was quite a discovery by the time, and get a name of the discoverer, rather difficult name, Russian name, Cherenkov. It's called Cherenkov radiation. Well, he got Nobel Prize for that. Quite strange and astonishing personality. His career has happened in communist Russia in 20s and 30s, and he was of very simple origin. He was a son of peasant. Yeah, he could get some education, but that time, that time of revolution, the education was also a little bit speedy. So when he started working, he was very different from his older and more educated colleagues. There was a cultural gap. Besides, he wasn't really good character, not very good in communications. So he just concentrated on his experiments and went to his lab to study physics, not much talking to everybody. The discovery comes about his personal qualities. He has a natural gift to see very small amounts of light. They have estimated it and they find that his threshold of his eye was of the order of 1 quantum. So absorption of quantum in eye apple of Professor Cherenkov produced a feeling for him. Was a bit exceptional. So he looked at the light, observed in course of radiation, and he saw something. He has just observed something. And you have a colleague which has a difference, a cultural difference between you. You kind of distrust his education. Your colleague doesn't talk to you. Moreover, he spends hours in his lab, and when he comes out, he tells you that he has seen something which you cannot see because you don't have such powerful eyes. You have to believe him and you don't want to. But after all, the colleagues have believed Cherenkov and they actually identified the source of light which he had seen. That was yet in the early days of nuclear era. That was before making any nuclear reactor. If you make a nuclear reactor, then the light becomes very much apparent. This is a photo of a nuclear reactor similar to what we have at our campus. It is a water bed reactor. So what you see here are active elements where radiative decay takes place, and they just swimming in a water basin. Right. What happens here? Electrons, which arise in the course of beta decay, they have velocities closer to speed of light. They have larger energies, so they penetrate the metallic shield and they go into water. Their speed is higher than speed of light in water to a certain frequency region. So this is emission of blue light, blue glow. Judging from intensity of radiation, it is not recommended for you to swim in this water. The radiation level is too big. Very good. Let us have some theory. we have all tools to compute the intensity of transition. First of all, before computing this, one has to look at conservation laws. So what we have, conservation of momentum and conservation of energy. So K is a momentum wave vector, in more exact terms, wave vector of initial electron after emitting a photon with momentum, with wave vector Q. Its wave vector has changed. Now there's energy conservation. Now let's make it in numbers. First of all, it's reasonable to assume that Q is much smaller than K. Right. So we can linearize this equation. K minus E K prime. Let us see, that would be this, which means velocity of the electron times vector Q. And that has to be equal to modulus of Q. Right, so we reduce it to this equation. And now we understand that this eventually an equation for an angle, for the angle between the direction of K and the direction of Q. Right? So we understood, without making any quantum mechanical calculation, that a Cherenkov radiation is emitted in a narrow cone with an angle defined by the ratio of the velocities. Right? If C prime is bigger than V, then this cone just doesn't exist. If the motion is faster than speed of light, then it does. So perhaps some of you have figured out why do I have a fighter over here. I mean supersonic fighter. When a plane breaks sonic barrier, when it gets supersonic, it emits a shock wave, and the angle of the shock wave is eventually given by the same relation. All physics is the same. Very good, but let me get back to Cherenkov radiation. Matrix element we need to compute. Let me recall what is this, density of current and vector potential. Right, so we need to compute the element of vector potential for a state where one more photon with momentum K, momentum Q has arisen. All right. Here we are, we just get it from field operators. Let me indicate there's some R dependence. Right, there is also computation of non-diagonal element of current density. Right, so there is also dependence on R, and it involves velocities of electron in the, yeah, it's the same escape, Roy. The same escape. We know that since Q is much smaller than K, these velocities are almost the same, so we can just unite everything into a single velocity. So after that, we integrate over R to obtain matrix element. Look, integration of two exponents will automatically give us conservation law of momentum. So here we are. This is a matrix element. This is proportional to velocity of the electron, and here dipole moment is in the direction of velocity. Since electrons are not confined, wave function is extended, dipole approximation just does not apply, doesn't make any sense over here. This matrix element, we can evaluate the rate. So this is transition rate to the element of volume. Again, we analyze polarization. There is nothing which comes from polarization which is perpendicular to K and Q. And this gives us extra factor as it did in case of electrons. Right, so we can concentrate on a single polarization, and now we can integrate over the angle, which is here in delta function. In distinction from atoms, when we integrate it over delta Q, we need to integrate over the angle. Why is it so? Again, because the emission is possible only in a narrow cone. Fine, we integrate. This delta Q is still there, but we can always convert it into frequency. So delta Q is delta frequency divided by C prime in this case. And what we get is a rate of Cherenkov radiation from a single electron, the rate per frequency interval. Let us see. There is a small parameter here, alpha, which means that electron does not lose energy instantly, it loses it very rarely. Also, how about the total rate? We would have to integrate it over frequency, but that diverges. As you see, the partial rate does not depend on frequency. Formally, it diverges. What to do? One has to recall that the frequencies at which we have modified the vacuum and made light velocity smaller than light velocity in vacuum, these frequencies are restricted to atomic frequencies. Right. So this rate only persists if for omega smaller than omega atomic. So if we wish to estimate the total rate of Cherenkov radiation. That would be alpha atomic rate. So that will be rather fast. Let's see, that will be 10 to the minus 2, 10 to the 15. So these processes are rather efficient. Good. Let us talk about the color of Cherenkov radiation. Experimentally, it is blue. But if one looks at this formula, we see that number of photons emitted does not depend on frequency, which is typical for, which suggests that this is white light. However, if you would look at energy emitted per frequency interval, that would grow with frequency. So we will have more light at high frequencies and we would see it blue. And it is blue indeed. But what does it show? It doesn't say much about light. It's more about our eye. Our eye is kind of measures energy per frequency interval rather than number of photons per frequency interval. That's why the glow is blue. Very good. With this, I have done my presentation. If you really stayed with me till this point, you're a very good guy. Thank you for your attention. Bye.